Greetings. Today we're going to do a board repair, actually a pair of board repairs on these twin boards that you can see. These are power boards from the late 1980s Data East Pinball machines. There were two complaints on the board. They generate several regulated voltages. The transformer secondaries feed directly into here, and it generates all the regulated goodness that the machine needs to run. Now, these boards are identical. Well, they should be identical. If we look at the board markings here, this one, come on, light up. It's 520-5000-00, which probably means revision 0. And then we have this one, and this one, 520-5000-00. So these boards are supposed to be identical, and that's kind of an ideal situation in a repair because you have a reference board. I mean, it has different problems. If they had the exact same problem, not so much, but this one is missing the 5-volt regulated, and this one's missing the minus 100 volts regulated. And the reason the voltage is high is it uses gas discharge displays, which need an absolute voltage of 200 volts. So this generates plus minus 100 volts, and your voltage differential there is 200 volts, and that lights up the displays. Well, obviously with the one of the 100 volt supplies missing, the displays don't light up. And with the 5 volts missing, the processor can't start because that's the logic voltage. So I started out with this guy, which was missing 5 volts. Here's how the 5 volts should work. We have the transformer secondary coming in here, which is 9 volts AC on each leg, and the center tap tied to ground. So we're basically feeding this bridge, this full wave bridge rectifier with 18 volts. But then one of the 9 volt AC legs continues, goes to this coupling capacitor here, hits another rectifier here, and even though this is only 2 diodes, it is still a full wave rectifier. It's filtered, and then goes in and feeds the MC1, it's 723 voltage regulator chip. And then what that chip does, basically, because it doesn't have enough current output, it needs a lot of 5 volts, probably on the order of 2 to 3 amps. So it uses a pass transistor over here to deliver the 5 volts. So really all of this part does is it increases the current output capabilities of the regulator chip, but the regulator chip basically has feedback for the voltage that's being generated, and it does just as its name implies. It regulates the output voltage to 5 volts. So what I did was I measured first, are these fuses, or is this fuse, which is the leg, the 7 volt AC leg we're using, is that bad? No, we had 7 volts AC here. Feeding the capacitor, all good and nice. Then I checked to see if it's coming out the other end, and it wasn't. So I pulled the capacitor, I measured it, and it was open. So pretty much what happened here is this thing died and acted like the fuse to it was blown, and there was no voltage going to the regulator. So it wouldn't work, so it wasn't generating 5 volts. Very simple. I pulled out the capacitor, replaced it, and boom, we got 5 volts. One of the more easier repairs, it took me like 10 minutes to find a replacement capacitor and replace this one on the board, but that's because yes, I have a lot of parts now and it's getting kind of difficult to find them. I wish I could be better organized, but I don't know how many more little drawer organizers I can fit into my around my workbench. But anyway, that got replaced, and we can actually try it out, make sure that the 5 volts is back. Another thing to keep in mind is this bridge rectifier here generates plus minus 12 volts, which is also used by the machine. They're 12 volts. They're both unregulated because they are only rectified, have smoothing caps on them down here, but then the voltage is most likely higher than 12 volts, but it's usually used for audio purposes, so that's fine. So let's have a quick look at this and make sure that we are still getting the 5 volts out of it. And here's a test setup. We have just an 18 volt center tapped transformer that through these test clips connects to the input, and that's all we really need. And now there are convenient test points over here that will let us measure the 5 volts as well as the plus minus 12. So let's turn it on. No noises, no smoke. We test the 5 volts. Yep, that fixed it. And while we're at it, we can check the unregulated plus minus 12. Here's the minus, and as I told you, they'll be higher than 12, but the voltages, the audio circuits that use these are not that particular about regulated voltage. And the plus 12, yeah, pretty much a mirror image of the other side. So this one was fixed. Quick job. Pat yourself on the shoulder and go on to the next one. Now on to the next board that was missing the minus 100. The astute observer will immediately see that this is the first board, the one we just repaired the 5 volts on. But let's just pretend that this is the second board, and the reason for that is if I use the actual board, the actual number 2 board, it would give away what the problem was, and it would take all the fun out of this video. So we're going to use this one, so you get absolutely no clues about what the repair was that I did. And so here's how the high voltage regulation is supposed to work. We get a 90 volt AC. We have a 90 volt AC secondary on the transformer that is not center tapped. One leg feeds in through this fuse. As you can see, it doesn't use the displays don't use a whole lot of current. The high voltage makes up for it. And then the other 90 volt tap is grounded over here, and it's grounded to common ground, so we have 90 volts AC on this line coming in. And then we'll see we got 2 circuits here that are almost mirror images of each other, except of course on one end we got PNPs, then we got NPNs, same here, but that generates ground. Is still the same ground, and we have minus 100 and we have plus 100 coming out. Plus 100 comes from the upper half, and that works fine. Minus 100 comes from the lower half. That didn't work fine. Now, brief analysis of this, it's really the same principle as with the 5 volts underneath. We basically generate, this is a pass transistor that is turned on by the pre-driver. Now the interesting thing here is there is no feedback from the output voltage back to the pre-driver, to the driver transistor. So this is just biased with a constant current over here, or constant voltage. It doesn't know what's going on the other side, but it just maintains itself. It's got a 3.3 volt Zener sitting at the base, and it's got a 100 volt Zener sitting at the base of the pass transistor over here. And this makes sure that the pre-driver turns on, and this makes sure that the pass transistor turns on. Of course, looking at this, you know, immediately I suspected the Zener diode, but I had to go through the motions and find out what was really wrong. Here in the middle of the picture you can see the high voltage part, which is this over here. Oh, these two caps also belong to that. And again, remember that even though I'm showing you board number 1, this one worked when I got it, and I'm not showing you board number 2 to take, so I don't take all the fun out of this. So you can sit there glued to your to your computer monitor and try to figure out what's wrong. So basically these are the pass transistors over here, and I know they look mighty small, but the whole system here is fused by a quarter amp fuse, so there's really not a whole lot of current passing through. Here is the this is the 5 volt regulator chip, by the way, which has nothing to do with any of these. These are the pre-drivers that bias these transistors on. And then we have an assortment of Zener diodes, rectifying diodes, and your general collection of capacitors and other stuff. This is the diode that I suspected. This is the 100 volt diode driving the minus 100, and this is the pass transistor. So I went in and I measured the pass transistor, and it was it measured totally bad in circuit. So I removed it and I measured it out of circuit, and it was still totally bad. I checked the Zener diode. Well, I checked it by simply doing a diode test on it, and I was getting a pretty high forward voltage. It was above a volt. So I took this one out too, and I measured it, and even out of circuit it was still above 1 volt, so that was bad too. And I did a quick check, I did a visual check, nothing looked bad. I did measure some of the resistors, and I did a diode check on the driver transistor, and everything looked fine. So I replaced the pass transistor, and I replaced the Zener diode over here. And what I used to power this time was I needed 90 volts AC, not center tapped. And for that I used the BK Precision 1655 AC power supply, which we repaired, well, a couple of episodes back. You know, it's ideal for that. So I hooked up the 90 volts, I turned it on, and this fuse lit up my workbench. This is the quarter amp fuse that supplies the high voltage section. I mean, that thing, it blinded me. It was so bright. So, dead short. Fine, I disconnected it, I checked everything again. This transistor had gone bad again. This diode was good. Nothing happened to this diode. So at this point, I started to measure components. I measured every single component in the high voltage area, both positive and minus. Anything that looked suspicious, I pulled off of the board and measured it off board, and I couldn't find anything else wrong with it. The ones that acted strange on board acted fine when having been taken off the board, so I put everything back in again, and I replaced this transistor. But I figured, I haven't really done anything. I mean, I've replaced this transistor. I had replaced it with a brand new one, and it just blew up right off the bat, so there was really no reason for me to try to power it up again, because this thing would just blow up on me. So now what I did was, and I should have done this earlier, since I'm using the BK Precision AC supply, it's variable. So why not measure the output, start with 0, slowly increase the 90 volts, slowly increase the voltage up to 90 volts while monitoring the internal voltage that's going across this guy, which keeps blowing up. So that's exactly what I did. I hooked up the 90 volts to this. Well, I hooked up the BK Precision to this, made sure it was set to 0 volts, turned it on, and while measuring the voltage here, I started to turn things up, the voltage up, very gently. When I reached about 70 volts AC input, we had reached 100 volts output. So there was something wrong with the regulation. Then I got bold and I increased it another 5 volts, and it wasn't regulating at all, because at that point the output voltage had gone to 110 volts, which obviously meant if I turned it all the way back to 90 volts, this thing would have given up its ghost again, because we're exceeding the voltage rating of this thing, and probably a voltage rating of everything else too, but this guy would sacrifice itself, blow the fuse, and keep everybody else alive. So now the big question was, why is this thing not regulating? I mean, I had to replace this pass transistor again. But before doing that, again, that was, well, I didn't have to replace it. It was still good but just to make sure, I replaced it again, because I had given it some voltage. It had been hit with 110 volts, and it doesn't have that high of a tolerance voltage-wise, so maybe this thing got stressed. So I put another one in and tried to figure out what to do next. I've checked all the components. I can't find anything wrong with them. So I did the next best thing, and that is, we must have a board fault here. So I did continuity checks, basically using the schematics and doing continuity checks on every connection that the schematic shows us, and see, is anything shorting to each other? Well, that took a while. My continuity checks turned out mostly okay, till I got to our suspicious component over here. The connections to, I mean, it's clearly marked ECB, but the C connection didn't make sense, and the B connection didn't make sense. And at first I couldn't figure it out, so I sat down and I actually drew a diagram of what this was connected to. And then when I stared at the diagram, what was revealed to me was that on this on the board, on the defective board, the C and B terminals were swapped. Yes, the C and B were swapped. I mean, in this case, on board number 1, they are properly labeled. But now, we can go to the guilty party. And on this one, it still says C and B. But then looking underneath the board and comparing the traces between board number 2 and board number 1, I could clearly see that those two terminals, or the points, connections on the board, had been swapped. How can that happen? I really don't know what to tell you. We checked the board designator or the board number that are identical. The top of the board looks exactly identical. But then, of course, looking closely at the back of the board, I realized that these two connection points had been swapped. So what to do is put another transistor in, and I swapped the collector and the base. And basically, you bend them in place and you put heavy insulation. Well, I put shrink. I insulated one of the terminals here, bent them over each other, soldered them into place, and then made sure that that the one leg wasn't pressing very tightly on the insulation underneath. And I think you can kind of tell that this leg has an insulation on it, and it goes to the center point, and this one just jogs over and goes into here. And I made sure that there is no chance of this shorting to this, that it wasn't shorting just out of the chute. And again, I made sure that there was some distance. You can't really see it from there, but distance between these two legs, so when this thing starts getting hot, there is less of a danger of these shorting. I've seen this done before, because there's for this transistor that's rated at 100 volts, it has a bigger brother that was used in some other pinball machines. But on those, the B and C terminals were inverted, so if you wanted to use one of these guys, you had to do this trick on it. But if you look at this one, this is all correct, so it's not like they used another kind of transistor here. These are complementary. But the traces on this board are different than the traces on this board. The board designator, you can see the 00 peeking through here, is the same. Well, my guess is that the board with the defect was like a first run or a prototype or something, and nobody bothered. Somebody found the error, and they just quietly fixed the board. And if that is the case, then I accuse them of stupidity because they didn't update the board markings. I mean, how can you release like an engineering correction to the general public or to the people who fix these, to the technicians, if you can't really tell? I guess it would have to say, carefully observe the back of the board and then show two pictures of what the prototype looked like, or the initial run looked like, and what the final run looked like. Anyway, so I couldn't, everything else was still good. That's the only thing I was able to do. And let's see if it still works. Alright, we're all set up. I got the BK supply hooked up, 90 volts AC. I adjusted to 90 volts AC. I double checked it with a digital meter. And here's output ground. And then we have minus and plus. I gotta admit, I'm still a bit gun-shy turning on the AC supply because I saw the smoked fuses and things destroyed. And looking forward to desoldering this guy again and checking everything else again, but we got to make sure it works, right? So here we go. Okay, it's on. I hid the fuse, but it didn't. You would have seen it if it flashed. So what we do is we check the negative voltage, and we're good. Minus 102. And right next to it, its brother, and that's still good. It's also 102. So probably has something to do with the bridge rectifier or these two caps, which are working a little too good. But it is regulating, because I did play around with the voltage. I took it down and it stayed stable until about 75 volts, and then the output voltage started to drop. So it's definitely regulating. You saw the voltages are good, and that finishes this repair. So now it should also be clear to you why I use board number 1 to illustrate what I did, because obviously if you had seen the crossover here, you would have guessed, as improbable as it seems, but that's basically what the problem here was. So what my advice is, I really don't know, because if this means that every board you repair you have to suspect the schematics, then you could never repair anything. It's an oddity. That's all I can say. It took me quite a while to find this one. It was very frustrating, but at least it got fixed. So thanks for watching. Please give me a thumbs up and a comment, and we'll see you again real soon. And one final clarification that I didn't get into. The pass transistor for the negative side is an MJE 350. Pass transistor for the positive side is an MJE 340. Those are the parts that I had, so it's not like that the transistor I was using to fix the negative supply was the wrong one. It was the right one. I triple checked the data sheets, and I think what more proof do we need than the first board, which had the transistors wired straight and worked perfectly.